Everybody, get my stuff. There's the attendance form, do the thing. What else? Oh, also, Sarah found a cool website. So here's a website where you don't have to download a thing, where you can go to plot. Yeah, I shaved. Yeah, you can go to the GeoGebra, whatever it's called, to that second link I gave you guys, and you can plot direction fields there without having to download P-Plane or anything. So that's an option if you would prefer to do that. It seemed like it would be maybe easier. Sorry. Maybe we'll use it a little bit today. Yeah. Anyway, all right. So I posted a quiz. Shouldn't be too terrible. And I've definitely, let's see, you guys have had some questions for me. Where'd you go? Some people asked about solving for C1 and C2 in spiral directions. Okay. So let's talk more about classifying. Sorry, that's not what I want to do. Classifying solutions to differential equations. Also, I was looking at the, let's see, where'd you go? At the Rademacher homework, I think. And he asked you guys some questions about like if a system is linear or nonlinear, which should be relatively straightforward. But then he also asks about if they're non-autonomous or autonomous. And autonomous just means that the differential equation doesn't involve the time variable, or I should really say doesn't involve the independent variable. So like I'm going to share my screen for just 1 second here. So looking at, sorry, I got all kinds of stuff over here. Looking at this homework assignment here, we're looking at this first question. So specify whether the system is linear or nonlinear and whether it's autonomous or non-autonomous. So this first equation is definitely autonomous because the differential equations dy dt and dz dt do not have the time variable in them. That's what it means to be autonomous. If you're looking at your textbook, I don't know if you guys have your textbook, but I was looking at your textbook on page, what is it, 632. They spell it out right there. They say that if your differential equations, they say slightly different words. They say if your differential equations are independent of time, then the system is autonomous. Whereas if they're not independent of time, or if there was a time or independent variable in there, then they would be non-autonomous. And so actually the second one would be an example of being not autonomous because the differential equations do depend on the independent variable, right? dz dx has an x in it. That means it's non-autonomous. So just want to make sure that's clear. So that's not really terminology we've talked about in class. So I just want to make sure everyone is seeing that. Excuse me. Where did I go here? So let me stop sharing my screen. Gosh, thank you. Yeah, I haven't cut my hair, but I have thought about it. The poll results definitely were mostly in favor of my wife cutting my hair, which sounds terrifying. But she's done it once before. It was okay. It was many years ago. So let's see. What do I want to say? Let's talk about some eigenvalues. So we're going to kind of we're going to live in the world where when I write a 2x2 matrix, we're going to assume that means that it's solving a system, that it's a system of linear differential equations. So for example, actually, let me do something real quick here. Let's see. Squared, okay. I want that to be small. Sure. This would probably be fine. 2, -1. Oh, that's interesting. Oh, 4 times that's much greater. Okay, I see. Sure. So here's a matrix. It is 2, -3, 4, -1. Can you guys see that okay? Oh, I don't have my video pinned. Sorry. I can't see it okay because I'm like, sorry, I don't want everyone there. So there's the matrix. And of course, so when someone writes this, you're just supposed to assume, right? We really mean this is, we've got this, right? We've got this, it's d x1 dt equals 2x1 minus 3x2, and dx2 dt equals 4x1 minus x2. Right? That's when someone writes this, they mean that. And you can use x1 and x2, you can use x and y, you can use whatever variables you like. So the thing here is that I want to find and classify, well, I want to find the eigenvalues, and then from the eigenvalues, I want to determine if I have a sink, a source, a saddle, if they're real, or a stable spiral, meaning an inward spiral, an unstable spiral, meaning an outward spiral, or a neutral spiral, if they are complex. So let's take a look. So I'm going to find the eigenvalues. So I'm going to do 2 minus lambda times negative 1 minus lambda minus negative 3 times 4 equals 0. And I get, let's see, I get lambda squared. I get a minus lambda minus, sorry, a plus lambda minus 2 lambda. So that's going to be a minus a lambda overall. And minus 12 is plus 12. And don't be fooled. So sometimes this will look like it's going to factor. This doesn't factor. So here my solutions are lambda equal to negative b, so positive 1, plus or minus the square root of b squared, minus 4 times 1 times 12, all over 2, which is negative 1 plus or minus the square root of 1 minus 48 is negative 47 all over 2. And I don't know how I got a negative there. That should still be positive 1. So there we go. 1 plus or minus the square root of negative 47 over 2, which is definitely imaginary or complex. Right, so my eigenvalues, lambda 1 and lambda 2, are complex, meaning we have some sort of spiral. And specifically, since the real part is positive 1/2, right, the real part being positive means it's going to be an outward spiral or an unstable spiral. Okay, so the other part that you guys have been asked about, I think, definitely in the homework that Ron offered you, is which direction this spiral turns, or whatever. What's the word he used? I don't know. What's the? God, I thought there was a better word for that than turns. I guess what's just the direction of the spiral? Is it clockwise or counterclockwise? And there's a couple different ways to figure this out, but the easiest way is just to think about plotting a couple points using your differential equations. So here's the easy way of figuring out which way it goes. Well, actually, I mean, the easiest way would be to plot it in p-plane, right? To actually just graph it. But if we're pretending like we didn't have that, like we just wanted to do it on our own, here's what I would do. I would probably look at the points 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. You probably only need like one of these, but it's good to have a few just to be sure. So if I plug in x1 equal to 1 and x2 equal to 1, right, this is x1, this is x2. So if I plug in 1, 1, here's what I get. I get dx1 dt equal to 2 minus 3. So I get dx1 dt is negative 1. And if I plug in 1, 1 here, I get 4 minus 1, which is 3. So dx2 dt equals 3. This means I'm going negative 1 in the x direction and positive 3 in the y direction. So from here, I'm going left and up. And already, I'm pretty well convinced that I am going counterclockwise. Right? There's no way from here that I could start going clockwise. But we can test a few more points. If you plug in negative 1, 1, now I'm pretty sure it's going to go down and to the left because it's going to continue the counterclockwise orientation. But if we actually plug it in, let's see what we get. So we get dx1 dt equal to negative 2 minus 3, so we get negative 5. And we get dx2 dt equal to -4 minus 1, which is also -5. So yeah, we're exactly going down that way. And you can keep doing it for these other ones. You probably get something like this and something like that. It's definitely going counterclockwise. And that's always a way that's gonna work to do it. So if you have complex eigenvalues, then you go back to your original equations and plug in like 1, 1, and maybe one other point and see if it's turning counterclockwise or if it's turning, ow, motherfucker, or if it's turning clockwise. Sorry about that. So that's kind of the idea here. Something else I want to say. Have any of your teachers talked about delta and tau, meaning the determinant and the trace? Okay. It's almost kind of worth talking about, even though they haven't covered it. Let me just. Do I really want to talk about that? I don't know. It's kind of nice.
For the unstable spiral, did you just put counterclockwise, or?
I would say the unstable spiral is counterclockwise. And oh yeah, I know what I wanted to look at it on the phase plane thing. So let me share my screen. So we look here. So this is this is in P plane. This is the link I just sent you guys. So we have x prime of t equal to 2x minus 3y. We have y prime of t equal to 4x minus y. Right, using x1 for x and x2 for y. And so totally, right, we can definitely see it's an unstable spiral, right? It's going outwards and is definitely going counterclockwise. That's cool. I like that. I mean, you could probably zoom out a little bit. You could, let's see. What does that do? I know what that does. You can make the, okay, whatever. Anyway, you can mess with this. I don't really know what all the things do because I'm just now playing with it. I don't like what I did there. I made a double, okay. Anyway, sure, that looks way better, okay. So that's kind of the idea here. So the other way you can, so there is another way of knowing this, and I don't exactly know why it's true. I was just trying to do the math earlier, but apparently, so in your matrix, 2, -3, 4, -1. Right, everything in this is A, B, C, D. If your eigenvalues are imaginary, then it's going to be counterclockwise if C is bigger than B, and it's going to be clockwise if B is bigger than C. Let me try to get that right. Counterclockwise. Yeah, just double checking. So if they're imaginary eigenvalues, then if this is the bigger number, it's going to be clockwise. If this is the bigger number, it's going to be counterclockwise. And the other thing that's also true is usually they're opposite signs. So it's really just whichever one is positive tells you the direction, right? If this one's positive, it's going to be clockwise. Yeah, counterclockwise. If this one's positive, it's going to be clockwise. I know what I want to do. There's another thing I had to send you guys. So here's a little link that explains most of it. Let me stop sharing. So let me send this to you guys. But that link I just sent you kind of spells it out as far as what happens if the eigenvalues are real or imaginary and how to get the direction of the turning. Yeah.
And
there is what's that?
What are C and B referring to?
Just so in the matrix, right? If the matrix is A, B, C, D, B is just the upper right-hand spot, and C is the lower left-hand spot.
Okay, gotcha. Thank you.
There is this other way of finding the eigenvalues that sometimes is actually easier. Yeah, I'm going to say this really briefly. If you guys want to forget about it afterwards, that's fine, but I feel like I should mention it. So we know the determinant of the matrix is A times D minus B times C, right? And the trace of the matrix is just the sum of the diagonal elements, A plus D. And I'm going to call the determinant capital delta and the trace tau, which is what your book does as well. Like, it's not just me. And so then you can find the eigenvalues. So here's my equation to find the eigenvalues. I'm taking, right, A minus lambda times D minus lambda minus B times C, right? The usual way of taking the determinant of this matrix, which is just this times this minus this times this, setting equal to 0. And then I'm actually going to solve that, and look what happens. When I multiply this out, I get lambda squared minus lambda A minus lambda D, which is minus lambda times A plus D. And then I get A times D minus B times C. But this is exactly just lambda squared minus A plus D is the trace, and AD minus BC is the determinant. So I just get lambda squared minus the trace of lambda, trace times lambda plus delta is equal to 0. And then I can just look at the quadratic formula in terms of the trace and the determinant of the original matrix. So I can find the eigenvalues by looking at that. And this is definitely something that's in your book, definitely something sometimes teachers talk about. And the reason it's nice is because you can see right off the bat kind of whether you're going to have real or imaginary eigenvalues. So I'm going to erase all this because this was just something I was trying to do to figure out something else. But here's what we can say. We know the eigenvalues are going to be real if the insides of the square root are positive, meaning if tau squared is minus 4 delta is bigger than or equal to 0, meaning tau squared is bigger than 4 delta, or the trace squared is bigger than 4 times the determinant. So that's kind of convenient, right? You can find the trace of this matrix and the determinant of this matrix really easily. So for example, well, actually, let me hold off on an example. On the other hand, we know they're going to be imaginary or complex if the trace squared is less than 4 times the determinant. And you can do, there's more you can do with this. You can actually find all sorts of conditions to be like, okay, well, if they're real, then we can determine if it's a saddle or a sink or a source by comparing what's happening kind of here and here, which is kind of nice. Yeah. But I don't think we need to spend too much time doing that. I really just kind of want to mention it. If you look in your textbook, I think all of this is talked about in section, where'd you go here? It's not that important. It's in one of these sections in chapter 10, I think. Yeah. Anyway. But for example, if we were given this matrix, I can tell really fast if my eigenvalues are real or not by saying, well, okay, my eigenvalues are equal to.
What is the matrix? 1, 2.
1, 2, 3, negative 5.
Thank you.
So my trace is negative 4, and my determinant is negative 5 minus 6, which is negative 11. And so that my eigenvalues are the trace, which is negative 4, plus or minus the square root of negative 4 squared minus 4 times the determinant, all over 2 times 1. That's negative 4 plus or minus the square root of 16 plus 44. And right away we can see, okay, our eigenvalues are real because the discriminant here, right, the stuff inside the square root is positive. So the eigenvalues are real. And I know at least one of them is negative, because I have a -4 plus or minus square root of 60. Well, the minus one's definitely negative. So we have one negative. Are they both negative? Well, no, because the square root of 60 is bigger than 4. So -4 plus the square root of 60 is positive. So lambda1 positive, lambda2 is negative. So already we know that we have a saddle because the eigenvalues are both real and they are opposite signs. Did we have to do it this way? No, but it is somewhat convenient. Let's see. Had something else here. 1 sec. Cool. So we've mostly, at least in our co-class, mostly just been talking about these kind of systems of linear differential equations where you don't have anything else but a multiple of x and a multiple of y. But we can change that a little bit. Actually, before I change that, let me give you guys, so I want you guys to try this one. So let me think for 1 sec. What did I do last time? I don't remember. So let's just make it like this. That looks dangerous. Let's not do that. Yeah, that would be bad. Let's try this instead. Okay, so I want you guys to find the eigenvalues for this matrix and then determine if it is, determine what's happening with the equilibrium point 0, 0. Is it stable? Is it unstable? Is it a spiral? Is it the sink? Is it the source? What's happening? Attendance one more time. There's something else to it. I also just sent a link to the online tutoring. If you guys want help and I'm not available, there are tutoring appointments you can make. So we can do this either way, right? We can find the eigenvalues either by saying, okay, 3 minus lambda times -2. Wow, that's a 2. Sure, that's a 2. Minus 6 times -3 equals 0, which gives us lambda squared plus 2 lambda minus 3 lambda is a minus of lambda. And then we have 3 times -2 is -6 plus 18 equals 0. So lambda squared minus lambda plus 12 equal to 0. I feel like this is very similar to something we just had. Oh well, it's fine. And so this doesn't factor. Yeah, I feel like I made this one with like the same eigenvalues. That's okay. It happens sometimes. So we get, again, Yeah, is this exactly the same? No, I guess not, or my brain is not working. That's all right, sorry. So right, we get lambda equal to 1 plus or minus the square root of negative 1 squared minus 4 times 1 times 12 over 2, 1 plus or minus. Yeah, how boring. It's definitely not the same matrix, but different matrices can have the same eigenvalues. So once again, we would have an unstable spiral because it's got a real part that's positive and it is complex. So let's see what to do. All right, well. Actually, sure. So let's go ahead and look at this one and talk about, so there's a lot of things we can talk about here. And except I don't want to talk about the eigenvectors because the eigenvectors are terrible. Right, so finding eigenvectors, I don't think you're going to have to find imaginary eigenvectors. I hope. Have you had to find any imaginary eigenvectors? I don't think so. I didn't see it in this homework assignment. Yeah. So, but there's also these other things called nullclines or isoclines. And so let's actually look back at what this equation is. So this is dx dt equal to 3x plus 6y. And this is dy dt equal to negative 3x minus 2y. And so the nullclines are just the places where each of the different derivatives is equal to 0. So, but they're lines, they're not just points. So if I set this equal to 0, I get 3x plus 6y equal to 0. And solving for y as a function of x, I'm going to get 6y equal to negative 3x. Y is going to equal negative 1/2 x. So I just get a straight line that goes from the origin. In a similar way here, setting dy dt equal to 0, I get negative 3x minus 2y equals 0. I get negative 2y equals 3x. I get y equal to negative 3/2 x. Also a straight line, and there are always going to be straight lines for these types of differential equations. But when they get more complicated, they might be less just straight lines. But for now, they're just going to be straight lines that go through the origin. So we can draw these. We can use some other colors. And you do want to kind of make sure you know which one's which. So this first one, that's the x nullcline. Y equals negative 1/2 x. And the other one was y equal to negative 3/2 x. I'm just going, over 2 and down 3. And specifically, on this line, dy dt equals 0, and on this line, dx dt equals 0. And what that means for our direction field is that along this green line, if dy dt is equal to 0, that means the change in the y direction is non-existent. That means that all of your arrows, all of your direction arrows should be horizontal completely because there's no y component to the arrow. Similarly, on this blue null line, this x null line, where dx dt is equal to 0, all of the arrows should be totally vertical, either pointing up or pointing down, because the dx dt part is 0, right? There is no change in x. And we can definitely look at this if we graph these, or if we go to the direction field thing. Let's see, let me throw this in here real quick. I don't remember what my equations were. Sorry, one sec. 3x minus 6y, 3x plus 6y. And the other one is negative 3x minus 2y. Share my screen. So looking at this picture here, you know, I think I might actually, so this is fine, you can kind of see, I guess you, so if you look here, if you try to look at the line, y equals negative 1/2 x, so if you go over 1, sorry, over 2 and down 1, but you can kind of see at that point right there that, sorry, right, so again, this is where dx dt equals 0. So if we're on this line, y equals negative 1/2 x, all of the little smidgy, like the little direction lines should be completely vertical. Let me grab p-plane, because I feel like p-plane, although I like, oops, that's not where I wanted to go. Let's go back. Sorry, where'd you go, p-plane? Now I need to open a new one of these. Direction field, p-plane. That's not the one I want to open. Yeah. So this one, this online one seems fine. I think p-plane looks a little nicer. If it would open, there we go. So graphing it here, let's see if I do the same thing. 3x plus 6y and negative 3x minus 2y. That's not where I wanted to put that, sorry. So we plot this. Right, so there's our spiral. But if we look, right, if we go, so starting at the origin here, we go over 2 and down 1, you can kind of see right there, like the tangent line would be vertical, right? And you definitely can see if you continue in the direction, right here, right, again, the direction field is straight vertical there, and it's going down. And if we go in this other direction, right, like right up, sorry, over, right, like right there, again, the tangent line is vertical. So that's what it means to be on a null cline. It means that the change in that direction is 0, so the change in, so all of the change is completely in the other direction. So along the x null cline, all the arrows are vertical. On the y null cline, all the arrows are horizontal. I feel like there's something else to say here. Let's see. So just because these examples are easy, let's go ahead and look at, so we're not doing the homework, but we're just looking at this homework. So I'm looking at like an example like this, right, where you've got a equal to negative 4, 1, 5, negative 5, and they're asking you for the null clines and the phase plane. So the null cline should be easy, right? So for example, for this one, and we'll talk about the phase plane in a second. So for this example here, sorry, we got negative 4, 1, 5, negative 5. I'm going to find the null clines first because they're not all the same, right? So I should figure out, it's kind of like a process of elimination sort of thing, right? Is it, which kind of null clines are it? So I'm going to have, you know, x dt is negative 4x plus y. I'm going to set that equal to 0, and we get y equal to 4x. So that's one of my null lines. So it definitely looks like it's either this first one or the second one, right? Because this line here, that looks like the line y equals 4x. None of these other ones have the line that looks like that. And then the second equation, dy dt equals 5x minus 5y equal to 0, is going to give me x equal to y, or y equal to x. So again, both of these first ones look like they could be the answer.
James, for the matrix for dy dt, it's 5x minus, is it 3y, or is it 3? Or is, oh, 5. Thank you.
Oh, sorry. And sorry. Sorry. I stopped sharing my screen. Yeah, sorry. I was just using that one there. So we know that it's got to be one of those two phase planes, but then we have to kind of figure out which way the arrows go. And I'm imagining the idea is not to just use some graphing tool, right? Like you should actually be able to do it without using the p-plane or whatever kind of thing. So how would you figure this out? Well, let's do this. And we'll come back to this one. Just tell me if we have a matrix for it. What is 3, 6, negative 3, negative 2? All right, so for this example, where the matrix is, what was it? Negative 4, 1. Negative 5, negative 5. We know we had y equals 4x. So, and again, I think, so here's what's going to happen eventually, you guys, is eventually there's going to be multiple null lines for each variable. So there's going to be like 2 different lines for the x null line, and maybe a line and some other weird curve for the y null line. And you're going to make sure you distinguish between the x null lines and the y null lines. So if you have some colored pens or something, if you're drawing them, it's good to draw them in different colors. So, right, here's my x null line. And this is where dx dt equals 0. Because again, that was from our equation, negative 4x plus y equals 0. So we got y equal to 4x. And then here's the other one. Right? This is where dy dt equals 0, which was just the equation x equal to y, y equal to x. And here's the thing you're going to see, or maybe have already seen. Wherever an x null line and a y null line cross is where you have an equilibrium, because it's where both of the differential equations are equal to 0 at the same time. But what ends up being confusing is if you have, like, sometimes you'll have like let's pretend, I'll erase it in a second. Let's pretend we had a third null line like that. And let's say this was a y null line. And what you'll see in the future is that this would also be an equilibrium point, because it's where dy dt is equal to 0 and dx dt is equal to 0. But sometimes people make the mistake of saying that this is also an equilibrium point, but it's not. Because right here, dy dt is 0, but dx dt is not. Right? So you have to have different null lines crossing to have an equilibrium point. If the same type of null line crosses, you don't have an equilibrium point. Okay, so now we want to figure out the phase plane. And really, the phase plane is just trying to figure out which way the arrows in the direction field are going. Now, here's the nice thing. We know that on dy dt equal to 0, all of the arrows are horizontal. They either have to point to the right or they have to point to the left. In a similar way, on the x null line, the dx dt part is 0. So all the arrows have to point up or point down. Here they're purely vertical, here they're purely horizontal. So now we have to figure out which way they're going. And I don't think there's a way to do it without testing at least one point. So let's test the point on this. Let's test the point 1, 1, right? So again, these are my equations. Dx dt equals negative 4x plus y. dy dt equals 5x minus 5, 4. So if I test the point 1, 1, which is actually on that null line, well, I know it's going to be purely horizontal. And then we get dx dt equal to negative 4 plus 1, which is negative 3. So at that point there, the arrow should be pointing to the left because dx dt is negative. And now here's the thing. Dx dt can only change signs when you cross one of its null lines, right? This is the only place where dx dt is equal to 0. That means everywhere on this side of dx dt is or of this null line, everywhere over here, the arrows are going to point to the left. Right? There's no other choice because they're never equal to 0 anywhere but here. And if you're not equal to 0, you either are always negative or always positive, right? So since we're always negative over here, we can't become positive until we're over here. So here, all of these arrows here are going to be pointing to the left. And let me think for 1 second. So I'm just trying to think, if x and y get bigger, this is going to get more negative. So my arrows are like bigger, but like I don't like to draw them super big, but so all the arrows on this null line point horizontally this way, but then all the ones down here are going to point to the right because over here they're going to change signs. And then we can do the same sort of thing for dx dt equal to 0. We could pick a point on it, like pick x equal to 1 and y equal to 4, which will make this 0. And then if x is 1 and y is 4, you're going to get 5 minus 20, which is negative. So up here, these arrows are going to be pointing downward because dy dt is negative up here. And similarly down here, once we've crossed this null line, these are going to be pointing straight up. And so then you can kind of see, all right, what's happening in each of these heads. Sorry, each of these 1, right, 2, 3, 4 sections. And so in this section here, we are definitely pointing up. And we're also pointing to the, sorry, I have to think about this a little bit when I look at it. So when I'm in here, right, I'm definitely on the side of the null line where I'm pointing to the right. I'm also on the side of the null of the, so let me rephrase things again. As far as the blue null line is concerned, I'm on this side of it, which means I'm pointing right. As far as the red null line is concerned, I'm on this side of it, which means I'm pointing up. So my arrow should be pointing right and up. So I'm kind of going like this. And again, my picture is not going to be excellent. Kind of like that. Same kind of deal here. Here I'm going to be pointing down. Sorry, I think I said left. I should have been saying right because clearly they're pointing to the right. Up here we're pointing down and left. So we're kind of like that. Again, you shouldn't be drawing all these arrows really. Out here, things are a little different. So over here, I'm on the side of the null line where I should be pointing down, but still to the right. So I should be down to the right, like, sorry, this is gonna look, so this is where I probably, right, down to the right. I don't really know. It's probably something kind of like this. But that's enough to figure out which picture we should be looking at. So if I share my screen again, you can see that, okay, well, look, it's definitely not this first one because out here, we're not down and to the right. And here, we're not up and to the right. It's definitely this one over here, where over in this section, we're down to the right. And here, we're up and to the right. And here, we're down to the left. And here, we're up and to the left. So you can kind of, what I'm trying to say in a lot of words is that these null lines section off which directions things are going. Right? If you're on one side of the null line, things are going one way. If you're on the other side, they're going the opposite way. So so for this blue null line, on the right side of that null line, things have to be going, sorry, brain, I almost had, things have to be going to the left. And on the left side of that null line, things have to be going to the right. And then for this red null line, this dy dt null line, we know that on one side of it, things are going up, and one side of it, things are going down, because on it, things aren't going up or down. And this is the dividing line between are we going up or are we going down. So on this side of the red null line, every arrow is pointing in a downward direction somewhat. And on this side of the red null line, which I didn't draw any, but, well, actually I did, I drew some right here. Right? All the arrows will be pointing up somewhat. It's just over here they're pointing up and to the right, and over here they're pointing up and to the left. Sorry, I know my pictures get a little bit wacky, but that's kind of it. And yeah, okay. So hopefully that kind of helps understand, helps you understand the things a little bit. Now, if we look back at this example, just to kind of go with it further, does it look like a does it look like a saddle, a node, or a spiral? That's a good question. I think it looks like a node because everything, it looks like a sink to me, right? I'm thinking that's a sink. Now, if I were really doing this, I probably would have actually found the eigenvalues, even though you don't have to, just because that's what I would want to do. But we can look at this and see that everything is pointing inwards, right? Clearly, if it was this answer down here, it's a spiral. This one is also a sink over here. And this one up here is definitely a saddle because some of the arrows, right along this path were kind of pointing inwards and this path were pointing outwards. What I just said was less than great. So, and here's why it was less than great. These null lines are not the paths that I should be thinking about. In fact, let's actually, let's go ahead and let me look at actually this equation because I want to show you guys two things. So, graph that thing. So there we go right there. So there's the whole thing right there. Now, okay. Sorry, there's something I need to know and I don't actually know what it is. It's okay. There's my, cool. So it looks like, that looks like an eigenvector kind of. Ooh, fun times, okay. So the deal here is that there are two eigenvectors, right? Just like there always are two eigenvectors. And one of them looks like it's probably about like this line here, right? Maybe like somewhere around there, right? Going through the origin. And one of them looks like it's this line here. Now I want to be very, very clear. Those are not the null lines. Right? The eigenvectors and the null lines are totally different. So the thing I said over here about them following this path, that's not really true. So the path they're kind of like just words, sorry. I meant over here. To see that this one's a saddle, I can see that we're kind of going, right? We're going in towards the origin and then away. So if I were to just travel along, it looks like maybe this line here, right? Can you guys see my cursor moving all right? Kind of. If you travel along that line there, which is not the purple line, right? Just some line I'm trying to draw, then that would be one of the eigenvectors. And if we travel on this line here, which is kind of close to the purple line, but not exactly, that would be the other eigenvector. And this second eigenvector would be the eigenvector that goes with the positive eigenvalue, because it's the one that's shooting you away from the origin. And this eigenvector, whatever it was, would be the negative eigenvalue associated with it because it's shooting you towards the origin. So, do I have anything else to say? So the null lines really separate kind of the graph and they help you see what's happening. If you want to, I think it's still worth finding the eigenvalues even if you don't have to. It kind of just helps you know what's happening. Or what I would actually recommend doing, like if you're doing a homework problem like this, is try and figure out which one you think it is first, And then after you've decided what you think it is based on your phase plane, then maybe find the eigenvalues to see if it actually is a saddle or a source or a sink. That's what I would say about that. So yeah, I guess that's all I've got to say today because we're out of time. But we'll definitely talk more on Wednesday. Let me know what you want to see. I imagine we'll need to talk more about this stuff. And yeah, that's all I got. And also let me know if there's any small videos you might like me to make. All right, I'll see you guys later. I'll make sure you fill out the attendance. Yeah.
Thank
all right.
you.